My name is Catherine Deverin, and this is Lab 5. The purpose of this lab was to evaluate the interaction between a falling magnet and a tube of aluminum foil, so that we could better visualize and understand Faraday's law experimentally and computationally, specifically the effect of changing magnetic flux on an induced current. In this case, the bar magnet was the source of the magnetic field and therefore the magnetic flux, and the induced current was produced on the aluminum tube and exerted a force back on this source of the bar magnet. With the bar magnet moving in the negative y-hat direction, it could be viewed as a magnetic dipole, with the tube modeled as multiple conductive rings layered on top of each other. A fundamental principle used was Faraday's law, which states that non-constant magnetic fields, in this case produced from the bar magnet, drives an EMF that induces currents in the surrounding objects, which in this case was on each conductive ring. The resulting induced current in each ring produces a magnetic field and force to oppose this change in flux acting on it. Therefore, it acts back on the falling bar magnet. Another fundamental principle is the Biot-Savart law, which states that currents produce a magnetic field. As shown in the diagram on the right, in this case, each current-carrying ring exerts a magnetic field and force on the falling magnet. We can apply Newton's third law to find what this exact force is. After 5 trials, I found that the average time experimentally for the bar magnet to go from the top to the bottom of the aluminum tube was 1.224 seconds, while computationally I got a value of 1.984 seconds. Experimentally, the bar magnet was dropped through a conductive aluminum foil tube and timed using video scrubbing software to get an average time of 1.224 seconds after 5 trials. With the computational model, our goal was to visualize the magnetic field source, the bar magnet, and the resulting induced current in the aluminum tube rings. That way we could calculate the fall time of the magnet and compare it to the experimental time. For the code, I first set my initial conditions that represent the geometry of the tube itself. Then, to find the magnetic field of the bar magnet, a distance r relative to the magnet, I use the equation for the magnetic field of a bar magnet acting on the conductive rings of the tube, which is represented by the off-axis magnetic field equation. Next, the next section of code was to find the rate of change of magnetic flux through each ring caused by the falling magnet, where I used the equation for flux itself as the flux is equal to the magnetic field coming from the magnet dot n hat times delta A. In this case, the distance was changing with time as the magnet falls. Next, I applied Faraday's law to find the current induced in each ring of tube using the equation shown in red on the right. This would be due to the changing flux of the bar magnet acting on the ring. Next, I found the force exerted on each current-carrying ring by the falling magnet using the equation that F equals I times delta L cross B, where I is the current induced in the ring, delta L is the circumference of the ring, and B is the magnetic field of the magnet acting on the ring. Finally, I applied Newton's third law to find the force on the falling magnet by the tube. This graph represents the resulting model from my code, where I found that the computational time for the magnet to fall was 1.984 seconds, which is greater than my experimental time. This graph represents the velocity of the bar magnet falling through the aluminum tube over time. This part of the experiment could have been more accurate by accounting for air resistance. As the bar magnet falls, the magnetic flux increases in the negative y direction. So that means in the picture shown on the left, the red represents the clockwise current, while the blue represents the counterclockwise current that is resisting this change in magnetic flux. If we flip the magnet, then the induced current would be clockwise instead because the change in magnetic flux would decrease in the y direction and it would want to oppose this. The shape of the graph tells us that the total net force eventually becomes zero because there is eventually no acceleration. In conclusion, if there is almost zero resistivity, the induced current would be much larger, as described by Ohm's law. Therefore, the magnet would take longer to fall through the tube. If there were holes cut into the tube, there would be therefore less rings in the tube. This less induced current and magnetic force would make the magnet fall faster.